Okay, let's have a look at we briefly mentioned last time at how Kw does actually change with temperature. What Kw is the ionic product of water. Okay, so we're looking at the equilibrium constant really for this reaction. So one water acts as a base, one acts as an acid, they exchange a proton. So Kw is equal to that. H3O concentration, H3O plus concentration times OH minus concentration. It's usually kind of simplified it down into this. We usually think about it like that, don't we? So I think I'll rub that out. Okay, and we remember that there's no such thing as H plus, it's really H3O. Right, and this equation is going to be very important as well. This is the equation for pH minus log of the hydrogen ion concentration. Right, so I think we established in the last video, we said that neutral is when OH, it's not pH 7 strictly speaking, is when H plus concentration is equal to OH minus concentration. So let's substitute that into there. So from that we get Kw is equal to H plus squared. So H plus concentration is equal to the square root of Kw. Now at 298 Kelvin, 25 degrees C, Kw is exactly 1 times 10 to the minus 14. So H plus concentration is equal to the square root of 1 times 10 to the minus 14, which is equal to 1 times 10 to the minus 7. And finally, we're going to use this equation here to work out the pH. So the pH is the minus log of 1 times 10 to the minus 7, which is, without a calculator, I'm sure you can do that, with 7. So the pH of neutral water at 298 Kelvin is 7.00, which is what we expect. Now, let's have a look at how the value of Kw changes with temperature. You can see that Kw here is actually getting bigger as the temperature increases. So water, of course, the highest, 100 degrees C, it's 5.13 times 10 to the minus 19. So how are we going to work out the pH? Well, we take the square. So H plus, just remember, H plus is the square root of Kw, and pH is minus log H plus. So do that, and you will get there. The pH of this one is 7.26. That, of course, is 7 exactly. This one is going down to 6.63, and this one is 6.14. Now, it's very easy to fall into the trap and thinking, well, look at this at 50 degrees C. The pH of water is 6.63, and you think, oh, that's slightly acidic. It's not acidic, because that is, strictly speaking, the definition of pH is OH minus is equal to H plus. And that is pH 7 at 298 Kelvin, but at 50 degrees C, it's not. It's like less than that, 6.63. Okay, let's see what Le Chatelier would have to say about this then. So I'll write this down properly, I think. H2O plus H2O goes to H3O plus and OH minus. Right, Le Chatelier, well, we can see that if we increase the temperature, Kw increases. So that means that the concentration of H3O plus and OH minus is increasing. So that means increasing the temperature is moving the equilibrium to the right. Now, if you increase the temperature, the equilibrium goes that way. Le Chatelier says, whatever you do, it will always try and oppose the change. So if you increase the temperature, it tries to decrease the temperature. So that means this must be endothermic in that direction. Okay, so the dissociation of water is endothermic. Now they've asked that quite a lot of times on questions. They've also said, you know, why isn't this acidic? They quite often ask that. So they come up fairly commonly. So just be aware of that. I remember somebody said to me once. They said, "Oh, well," I said, "Is you know, asked them the question, is it exothermic or endothermic?" And they wrote this down. They said, "Oh, so right, They said, oh, it's endothermic because you've broken a covalent bond." Which is true. You have broken a covalent bond between one of the oxygens and one of the hydrogens, yeah, but because they were just thinking of it as that equation, they were forgetting that really what's happening is this equation. And what we're doing there, yes, you do break a bond, but you also form a dative covalent bond in the H3O plus, don't you? You're forming a new covalent bond between an H plus ion and the water molecule. So yes, you do break a bond when you go forward in this reaction, but you're also making another bond. So you can't tell from that alone whether it's endothermic or exothermic. But if you look at these values of Kw, you know, we can see Kw getting bigger, so it must be endothermic in the forward direction.